Whom of you are electrical engineers? 1, 2, 3, 4, 5. And whom of you are physicists? 1. Whom of you are biomedical engineers? Most. Whom of you are chemistry students? 1. What did I miss?
Sorry?
So which discipline did I miss now? Who hasn't been? Chemical engineer. Okay, so not a chemist, but kind of something like it. Okay. Now I myself actually am a pharmacist, so totally different again. So I can say many things wrong, as you will see. Okay. So Severin has given the first 2 lectures. I will now give the next 2, I think, and after that, me and Mathieu Odijk will go on with the lab on the tube. So today I want to talk about microfluidics. Tomorrow will be nanofluidics, microscale, nanoscale, and I will talk about principles of flow in microsystems, and then I will talk a little bit about applications. So this is an overview of what I want to talk about today. So the basics of viscous flow, which people also call laminar flow. Then I will talk about a Reynolds number as an example of a dimensionless number. Then I will talk about mixing in microsystems, pumping and moving liquids, 2 different types of flow, different from pressure different flow. Then a little bit about micromachine pumps and filters, and finally about microsystem integration concepts. Close the door. Okay, so first some basics of viscous flow. Now, what we're going to do together now is to deduce some equations that are about pressure-driven flow in microchannels and microstructures. So we have, for example, a pump, Syringe pump, and we push liquid through a microchannel. What happens then? Now, what you will see is that generally viscosity is the dominating force, you can say. And that makes the fluid flow in parallel layers, as you see here at the bottom. So instead of turbulence, where liquid loses track and flow lines turn back and go towards the wall, etc., etc., in laminar flow, liquid is very nicely organized. And you call it laminar flow, so like in lamina, in sheets. And they don't mix these flow lines. There's just mixing by diffusion, as we will see. Now that's why you call it laminar flow. However, in large channels or high velocities, you get turbulent flow, as you see in the top. Now we'll talk about these 2 regimes today. So this is our typical microchannel. So liquid flows from high pressure to low pressure. And here I showed more or less what's going on. So these are these laminae. So you can subdivide the liquid. You know, that's not real, of course, but you can, for the image, subdivide it into different tubes that have friction between each other. And then if you would look at the center tube, the force that propels it is the pressure at the back of the tube. That is multiplied by the area. And then it has friction on the outside of the tube. Friction with that tube. So this one slides within the tube around it. And now, for this one, the frictional perimeter is quite large with respect to the area. So it doesn't move so much faster than the tube around it because it has a lot of friction. It's small, so it has a lot of perimeter for area. So that one doesn't move much faster than that one. If we go to the outside one, it has much more area over perimeter. So it moves much faster than the immobile outside of the tube. Now, that's the reason you get a parabolic flow profile. So the smaller your tube, the larger the perimeter with respect to the area, and the same pressure therefore can't move it really very fast with respect to the one outside of it. So friction increases in relative contribution when you downscale the tube. You get a parabolic flow profile, and you can see that here they have had a fluorescent dye. They made a picture, they started with a plug, and after a little while you see fluid at the wall moves very slowly. Slightly in, it already moves a lot faster, and in the middle, not so much faster than just over there. So if you downscale the tube, you just end up with this little bit of flow. So much smaller than the tube, which is just 2 times smaller. Now, how can we describe it by physics? Okay, so pressure-driven flow. You exert a net force by a pressure gradient. So here we have a pressure gradient. P is the pressure there, and here is the pressure P plus dP dx times dx. So we have a gradient of pressure dP dx, and that makes the pressure a little bit higher over here at the distance dx from here. So the force, pressure is force per area. So we multiply with the area to get the force. So here's the force PdA. dA is the area here of this little parcel of liquid. On the right hand side, pushes back, but here the pressure is slightly different because it's pressure plus the PdX, gradient of pressure, times dx. And of course again, times dA, because we look at the force, so it's pressure times area. Okay, that's a very complicated way of writing it down, but that's important. So we'll be looking all the time at a little parcel of fluid. Now, so the pressure force is that one minus that one. And that's what you get then, the PdX, that one, and we take that one off, so the P disappears. The PdX times dx times dA. Now dA dx, area times length, is the volume. So it's the pressure force is the gradient of the pressure times the volume of the parcel. So if we divide by the volume, we can see that the force per volume, Newton per cubic meter, is equal to the gradient of the pressure. Now this is Newton per square meter, so it's Newton per square meter per meter, so that makes sense. So we can talk about the force per volume, and we'll see later that other forces are also, you can express them easily as a force per volume. So by a pressure gradient, you get a certain force per volume of particle, and that is equal to the gradient of the pressure. Just a little bit more force on the left-hand side than on the right-hand side on this little parcel of liquid. Now, of course, everybody from secondary school, they know if you exert force on something, it will accelerate.
Yep.
So there it goes. F is m times a. So this is our force per volume. This is m times a, acceleration, the change of velocity with time. And of course we had the force over volume, so also here we do the force over volume. Now, force over volume is density. So we express density by the rho here. So the force per volume is the density times the acceleration. Okay, so we will accelerate. Now, what do you think? Will it go on accelerating forever?
No.
No, why not? Friction.
Yes.
Now, if you got a parcel of liquid, what will it have friction with? If I have this little piece of liquid somewhere in the fluid, and I exert a force on it. So where does the friction come from?
In the channel that is flowing?
Sorry?
Yeah, surface.
Surface, yes. So the surface of the tube doesn't move. And if I got a parcel of liquid in between other liquid, does liquid also have friction with liquid?
Viscosity.
Yes.
The viscosity with the liquids.
Yeah.
Molecules.
Yeah, so liquid molecules, they stick together.
Yep.
And if you want to push one past another one, or a little volume of liquid past another volume of liquid, they stick. So
together.
It's a little bit hard to move it. Now, so indeed, with increasing velocity, the friction with the wall and the surrounding fluid increases. And very soon, you get an equal force in the opposite direction. So this is our pressure force per volume. And very soon, the acceleration stops, because we have a friction force in the opposite direction. Think about it, you on the bicycle, you exert the force, you accelerate, but at some point in time you go with a constant velocity because there's lots of wind against you and the friction of your tires and stuff like that. So you can go to some velocity determined by the friction actually at that moment in time. Now, how do you characterize friction in liquids? And that people found out there's a concept which is very useful there, which is called viscosity. And viscosity characterizes the intensity of the viscous friction. So how do they determine the viscosity of a fluid? Well, they put it in between two plates, and they have a certain distance between the two plates. They put a fluid in between, and they move the top plate with respect to the bottom plate with a certain velocity, V0. And they find that the force they need to exert per area is equal to the velocity difference between the two plates, which is V0, because the bottom one has a zero velocity, divided by the distance between the two plates, and multiplied by the viscosity of the liquid which is in between. So for every liquid, the force is different that you need to exert to move top plate with respect to the bottom plate with a certain velocity. And some liquids have with some liquids we really need a large force. For example, with molasses, stroop, it's very viscous, so you need a big force. With air, you only need a very small force. And water is somewhere in between. Now, that's the viscosity of the liquid, which determines that. So, higher velocity, higher force, smaller distance, higher force, higher viscosity, higher force. Okay, now for a tiny parcel of liquid, if we move the top plate of the parcel with respect to the bottom plate, we can write down exactly the same equation, but now for the small particle. So the little force per little area, the FDA, is our viscosity times the change. Now this is a tricky one a little bit, because if you get your head around that, you understand a lot more. What you see here is dVy, the x. So there are two dimensions there, the y dimension and the x dimension. So you move the plate in a y direction, which we call the horizontal here. And the change of velocity in the y direction, the change of it in the x direction, so how much faster do I move the top plate with respect to the bottom plate? Yeah? When they are quite close, what's the gradient of velocity between the two? That determines the force that I need. So it's a change in velocity in that direction over that direction. Here I have a velocity 0, for example. Here I have a velocity v. So it's a change of this velocity in that direction over that direction. Okay. Now, when I got the liquid parcel, somewhere in our liquid I have friction not just with one surface, but with two surfaces. One on top of it and one under it. So it's a complicated situation, because I don't just have one ball, I have two. How can I describe that? Now, let's say I have a linear velocity profile. So our parcel moves just as much faster as the top parcel, as it moves slower than the bottom parcel. Now what do you think in that case? Will there be a resulting force? If the top parcel moves slower than our parcel and the bottom one just with the same amount faster, will I have a resulting force? Anybody?
It will
So,
be very small.
what do you think? What determines the force by friction? So if something moves a lot faster than the other one, will it drag it along? What do you think? If there's friction between the two. If I do this, I drag it along by having a little friction, friction here, isn't it?
Yep.
Okay. Now, so by friction I can exert a force.
Yeah.
Now if I at the top move faster and at the bottom I move slower than my parcel, and I move with the same velocities faster at the top as I move slower at the bottom, will there be a resulting force? No, eh?
No.
Yeah. Okay, that's what I'm going to show, that indeed there is no force. So here at the top I have a velocity difference between this one and the parcel at the top. So here I have a friction force. which is equal to our viscosity, times the velocity difference there and there, so the gradient of the velocity between that parcel and that parcel, that's dv dx at this first area, times our area. You remember, right? That's our definition of viscosity. df dA is the viscosity times dv dx. That's dv dx, that's the viscosity, and df dA, so I multiply both sides with dA. So that's for the top. And that force is to the left, because this one moves faster than that one. So the force is to the left there. Now the bottom one moves faster than our parcel, so that one is to the right. And actually here, the second force is again same as that one, but now to the right. And dv dx in both places is the same. Because here, dv dx is that difference, and there it's that difference, and we got a straight line here. So, our total force is 0, because the bottom one drags it to the left, and of the top one, and the bottom one drags it to the right. So a linear velocity profile, there's no net force from it. So how can we exert the net force by viscous coupling? Now, we can if the velocity profile is not linear. And so in this case, here, the difference between the velocity between the top parcel and our parcel of interest is large. So here, there is a large frictional force to the left. At the bottom, the velocity difference is only small. So there is only small force to the right. So there is now a resulting force, and actually it's to the left. So, because our particle really moves fast with respect to that one, so that one will keep it back by the friction. And if you write it out, then our resulting force is the summation of the two forces. Now the top one was equal to the viscosity times the velocity gradient at the top. The bottom one is equal to the bottom one times the velocity gradient at the bottom. So what I will have is the viscosity times the gradient of the velocity gradient. Because it's a change of the velocity gradient over this little distance dx, so that's the gradient of the velocity gradient. It's the second derivative of the velocity gradient. Times dx times dA, that's our volume again. So the viscous force is equal to the second derivative of the velocity. It's the change of the velocity gradient over the size, over the length of our particle. Okay, and you can write it in 3 dimensions if you want. So in general, and that's actually in general very nice, if you have a convex flow profile, which means in the direction of movement, the flow profile has a curvature. Then there is a net viscous force working against the flow direction. And check this at home, if you have a parabola, or whatever type of curve thing, you take the second derivative, it's negative. If you got a concave one, it's positive. But for a parabola, or any thing with a positive curvature, you have the second derivative is negative. So, and it's logical, because there is my force pushing it forward, so I'm somehow get my friction must be backward. The frictional force must be the opposite side of the force that I exert on my little parcel. Okay, so I had a force on this parcel. You remember the pressure gradient? That gave me a force per volume, the gradient of the pressure. And now I have the viscous force. So I find that in order to get this viscous force, I somehow will get a curved velocity profile. Now that is, when we now take the 3 forces that we have been discussing, acceleration, the pressure gradient, and the force from the viscous coupling, you get a so-called, well, this is part of the Navier-Stokes equation. There are even more terms in the Navier-Stokes equation. But now we kind of now derive the simple form of the Navier-Stokes equation. So energy input by the pressure gradient can be used to accelerate and to create friction. Initially, you get acceleration. Now, in large systems, you will get very high velocities. We will see that later. We get turbulence. But in small systems with much friction, we quickly reach a steady state with a constant velocity, no acceleration anymore, dv dt, 0, and only frictional forces will be important. And then this will be the equation that we will be dealing with in microsystems. Pressure input and friction. That's it. So that's the Navier-Stokes equation for steady state, incompressible viscous flow. Incompressible means we're not working with air, which you can compress. We're working with water that you can't compress. Otherwise it would be another term. And then we can start calculating. I will give you this slide and you can look at it at home. It's basically starting from this one and some boundary conditions. You can integrate it. You know that at this point dv dy is 0, so there's no change of velocity in the middle of the channel. And the second boundary condition is that the velocity is 0 at the wall. And then you calculate that that is the velocity profile. And then you should note that in the middle of the channel you call it y is 0. So in the middle of the channel this y is 0. And the velocity is the highest. Now the pdx in that direction, in the x direction, the pdx is negative because when we go further and further down the channel, the pressure becomes lower and lower. That one is negative. Then we got minus a squared, so the velocity is positive in that direction, downstream the pressure. And we have a parabolic flow profile, y squared. So you can do this at home, calculate it, and you can also do that for a slit. Oh, so that's that one, we already did it for a slit. In a cylinder, you get almost the same equation. And you can also derive it for another situation where you have, which is the same one as when we wanted to find out about viscosity. So we take two plates, we don't apply pressure, but we actually just move the top plate with respect to the bottom plate. Then you get this linear flow profile. So it's actually no, you remember, there's no pressure gradient. You don't need a pressure gradient in that case to exert force. You exert a force at the top plate. Okay. Now, these are the velocity profiles that you have here. So you can calculate the velocity in the y direction with this equation. By integrating it, you can get the average flow velocity in the slit. And this is the average flow velocity. Very useful equation. You can use it a lot. You will use it later when you start designing. In 2 lectures you will be designing your own microsystem. Then when you make a slit of height h, or any microchannel where the height is much smaller than the width, you use this equation to calculate the average velocity. You can learn it by heart, quite useful. The same one for a cylinder of radius r, average velocity. So the two are not very different. Important point to see here is that the velocity scales with the height squared. So if you make a microsystem 10 times smaller, the height, the average velocity is 100 times larger. 100 times smaller, and the same pressure gradient. So to keep reasonable velocities in microsystems, you really need to have high pressures, which is a limitation. We'll later see how to overcome that limitation. Okay, dimensionless numbers. So here is laminar flow that suddenly becomes turbulent. Now, so it's kind of unstable in this system. So how come? Now, you can calculate whether we call this nice laminar flow that we have just been talking about, or turbulent flow, by a dimensionless number, which is called a Reynolds number. So, who of you are familiar with dimensionless numbers? All right, okay, so that's kind of okay. So you will already know what type of